Now let's see that Laplace transform for electrical systems. So for electrical systems, we have linear circuits. What does linear circuits mean? It means it's consisting of passive elements or linear elements like R, L, and C. So let's look at this. We have a resistance R, right? We have a capacitance and inductance. Now what we would like to do is that we would like to convert these elements into the frequency domain. Now, or the S or complex frequency domain, which is the S domain. Now you will ask me how I am going to do this. Now look carefully here. For this equation in the time domain, it is V equal to I multiplied by R, right? This V as a function of time and current as a function of time. So V of S will be I of S multiplied by the resistance itself, because the resistance is a constant value. So you only get Laplace transform for current and Laplace transform for V. So the equivalent system will be V and I and the same resistance R, same as normal, nothing changed at all. Now let's look at the second case here. So we know that V is equal to, or the current in the capacitance is equal to I equal to C dV by dt, right? So this is the equation of current in the time domain. Can you convert this equation into frequency domain? Yes. The current will be I of S, Laplace transform of the current itself, multiplied by C is a constant value, multiplied by dV by dt, derivative of voltage with respect to time, is S multiplied by V of S, right? Derivative is converted into S, which is the S of the Laplace. So you'll find that V itself, V of S, will be I of S, and take this to the other side here, so it will be CS, okay, I divided by CS, okay. Now this is equivalent to I multiplied by XC, which is the reactance of our system. So XC is 1 over SC, which is the equivalent impedance or reactance of this capacitance. That's why, if you remember from the AC circuits course, okay, we said that the equivalent, when we take a capacitance and get its equivalent, we say that it is XC, which is 1 over J omega C. If you remember, this J omega, 1 over J omega C, came from Laplace transform, okay. Why? Because you can see current multiplied by a certain impedance or reactance. Now similarly as here, we have V equal to I multiplied by R. So here V will be I multiplied by 1 over SC, which is our XC. Okay, now in the steady state, you will see that we replaced in the AC circuits, we replaced S with J omega. Now why is this? Because you will find that S is equal to sigma plus J omega. And when we analyze our AC circuits using KVL, KCL, we analyzing it in a steady state, right? So we don't have the transient response of the exponential when we are switching on or switching off. That's why when we analyze it in steady state, we put the damping factor sigma equal to 0. So we will have only the oscillatory response J omega. That's why we put S as J omega in steady state when we have a supply. Okay. What about our reactance? For the reactance with the same idea, V is equal to L di by dt. So V of S in Laplace domain is L, which is a constant, multiplied by derivative means S multiplied by the current in the S domain. So it will be equal to the current multiplied by SL, which is the XL or reactance of the inductance. SL, as you can see here. Now you will see that in electric circuit again we substitute with J omega L, if you remember from the AC circuits course. Again, why J omega? Because S sigma will be 0 in a steady state. Okay, this one gives us the transient exponential behavior. Okay, so I hope you now understand how can we represent these elements R 1 over SC and SL in the S domain. This helps us to deal with this circuit normally without the integration or differentiation, as we will see in the next lesson. Okay, now you can see that when we have impedance, so impedance in electric circuits in Laplace domain is simply Z equal to V over I. Now this Z is simply equal to root, okay, as a magnitude, root the resistance square plus XL minus XC all square. Okay, now if you remember, where did we get this? Z itself is represented as resistance plus J XL minus XC. Okay, so their magnitude will be real part square plus imaginary part square. Now again, where did this came from? Remember that we have here capacitance 1 over J omega C, okay, and this one is J omega L. So this one omega L itself is J XL, and 1 over omega C is XC, and 1 over J, or 1 divided by the complex imaginary number, it will be negative J. That's why when we combine these imaginary part, it will be XL minus XC, as you can see here. The second type, which is not linear circuits, like operational amplifiers, like inverting, non-inverting, and etc. We call these elements passive elements, and we call this active elements that require a supply. For example, this is for operational amplifiers, which we discussed before in our course for electric circuits. We said that if we have an inverting amplifier, you can see a negative sign here. When we have an inverting amplifier, then V output over V input, output over input, is simply negative the second resistance divided by the first resistance, R2 over R1. Now similarly, if you have, let's say like this, a capacitance here 1 over SC, then it will be negative this parallel combination divided by R1. We will see this in the next lesson. Now of course, in this is very important, similar to time domain, in the S domain all rules of KVL, KCL can be applied normally without any kind of issues.